Anyways, so that's the apocalyptic setup. But on a kind of a brighter note, I mean, this project is really about kind of enabling smart grid architecture exploration, right? So the problem isn't really like trying to solve any particular problem in power systems or like smart grid, but kind of trying to reason about the whole architecture and how it is that all these like projects that are involved trying to kind of simulate different pieces specify and exchange their models and data, right? So here this is a picture from the NIST Smart Grid Framework. This picture represents like a 250-page document that kind of talks about each of these bubbles in detail, or clouds maybe they are. But I mean the point is that back in the day, you had kind of centralized bulk generation and then downstream dedicated consumption, right? But we want to move to a model where downstream at your house you can have solar panels, or your car with the your Tesla with a battery inside of it, participating in this grid in a meaningful way. And I think the thing that's important to emphasize here, if you look, there's like the dotted lines are the actual power flow. That's like the real power system stuff. But the enabling part and the challenging part of this is all these solid lines, which are secure communication flows. But the idea of how do you like coordinate, control, how do all these things factor into actual day-to-day grid operations? And if you really think about the vision of kind of smart grid, what's really important in some sense is this markets bubble here. It's like how do you incentivize utilities, especially in the US, to kind of incorporate kind of renewables into their business model, right? It seems kind of at ends with their current setup. So I won't go into all that detail, I'll just kind of stay down in these bubbles down here. But so this is the NIST one. Here's a picture from one of the European standard organizations diagrams. So their clouds are a little less fancy. But it looks pretty similar, except they really wanted to here pull out their own bubble. It's called DER. So here we added this to the NIST model. DER is the BUZZ acronym for distributed energy resource. So it's supposed to be like an abstraction that's able to kind of capture all the relevant properties about wind turbines, PV systems, batteries, all these kind of things, and package them in a way that's relevant for when you want to communicate. Here they're imagining that the DERs only participate in the distribution, which is like the medium to low voltage part of the grid. Transmission's kind of like moving power around regionally at a high layer. So Europe says that, and then NIST says, yeah, okay, we'll stick it in the same cloud, not give it its own cloud. But so this is, as you can see, a draft of like the next one. So the point here is that if you zoom into any one of these clouds, there's tons of standards going on that kind of provide guidance on like specifying, exchanging models, information, how it's done. And this is like the real problem we're focused on, and that a key aspect of this clearly needs to also be able to evolve as time goes on, right? We're already changing. Okay, so we're going to zoom in here to this like DER blob. Let me just say how it's done right now. There's this common information model, which is not unique to power systems, but there's a set of standards that focus on utilizing that in the context of power systems. And they're basically UML-based kind of models, and then they use XML for their model exchange. And then there's a whole bunch of other standards that are kind of related in really complicated ways to all the things going on in this diagram. Okay, so our approach here is just to take some techniques from categorical databases, which kind of have been pioneered by guys like Mike and David, and apply them to this kind of problem model management. We're also not the first ones to think of this. So the setup is just finally presented categories as model schemas, set valued functors as instances. As you saw Ryan talk a little bit about, then when you have functors between the schemas, those will induce functors between the instances. So you kind of get those for free, and they're implemented in this CQL tool. And then we kind of just talk about how do we use those to kind of specify models and then connect different models to one another and then connect those models to tools. So that's the MO. Okay, so here's your basic setup for like a distributed energy resource. So here it's just like a state transition system. So you have different states your thing can be in. Here you have your air conditioner. HVAC is the acronym for air conditioner. It's either just on or off. And P and Q here are like the real, they call it real and reactive. They're the real and imaginary parts of power. So in AC power, resistance, current, voltage, and power are all complex valued quantities. And so here we have something like a battery, which can go into like negative P when it's discharging, so it's like spitting power back out. So okay, so here's just like your kind of little schema. They represent this kind of like data type, and you can kind of reason about doing fun things with it. So okay, we'll just start drawing them in this little boxy way when you have these kind of these things here, they're called entities, and these guys here, these attributes are like taking value in some type system, but we'll kind of not worry about that. So that's like zoomed all the way into this like distributed energy resource level, but Oh yeah, I should say we implement all this stuff using this tool developed by Connexus AI, this CQL language, which you guys already heard all about. So here's just like me perusing through some papers in this area and looking at the types of models they build. So there's kind of like, on this side here, you see just like two different models of these distributed energy resources that just share like the common base model of thinking of them as state transition systems. So some people want to assign kind of a virtual cost to transition. So that's kind of just like, my DER tells me how willing it is to kind of turn on or off, right? And then I want to solve some optimization problem there about, retasking my DERs in order to respond to some change. Over here, maybe people are really interested in kind of reasoning about failures in some of these resources. So here, maybe you have some kind of Markov model. So in this half here, these guys like share like a method, kind of like we're going to use Markov chains to model the behavior of the system. So here they're like, the states here are kind of like working or failure mode. Right, and then you kind of assign transition probabilities there and maybe use the steady states to calculate expected values for reasoning about kind of collections of DERs. Over here, people want to like worry about the, the stochasticity and the inputs that force a lot of these distributed energy resources, so like variability in wind, water. So in there, they'll like use a Markov model there to represent where like the states are just like different speeds and you have transition among those states. So here they'll use that sometimes for like take data, try to infer a Markov chain from it, and then use that to like sample and create new data for like problems in system design. But the point is you can kind of specify all these things in CQL, and what does it really enable? Well, in some sense, you have groups that kind of spend a lot of time trying to build realistic DER models, right? And so in this sense, when you define these kind of functors here on the instance level, you can use these combinations of the sigmas and the deltas that Ryan talked about to kind of just like take the base model from there and kind of extract it over to your other side. So it's like a technique for starting to build up a model repository of these kind of DR models. Over here, you're going to like use the same tool to like compute the steady state. So maybe that's like, I don't want to do that. OK, so now we're going to zoom into this guy here. This is like the distribution level, and this is like where you want to just kind of spread power around at like the kind of regional or like somewhat local level. And so in here, this is like the first thing you would see if you open like a power systems engineering textbook. It's like you have some, again, this kind of network here. They like to call the nodes buses. And there's some kind of lines connecting them. And then these buses come in different types. And the way you can think of it is that this PQ bus is just like a typical load, right? And all that means is that as an input to this, you kind of tell me what the demand in terms of the real and reactive power is of my node. These PV buses are like generators, right? It's like, I have some ability to produce power, and I'm going to try to do it at a constant voltage. So those are like inputs already. And the kind of free things are whichever other pair you didn't specify. Right? So the variables of interest are the real and reactive power. And then here, voltage is also a complex quantity. The V is the magnitude, and theta is the phase. So welcome to engineering. They like to use mixed representations of complex numbers, right? So down here are like the power balance equations you would get. So here, the i's and j's just index the buses, and theta ij is just the phase difference. So you get some kind of complicated nonlinear set of equations that you want to ensure, that you need to evaluate in order to figure out what like the feasible operating regions of your grid are. Okay? These G and B here are like the generalizations of resistance, so impedance they call it, right? So this is like telling you how hard it is for current to flow through your branch. Okay, so really it's like way more complicated than all that. And you can see here in this kind of diagram, you have all these other attributes that you need to really specify one of these problems. So things like max voltage across your line, or like max current through it, or some kind of type system, or which zone my bus is living in, so on and so on. So what do we do? Oh, there it goes. Yeah, so here we just looked at a particular tool that's pretty commonly used mostly in like the academic power research literature. MATPOWER is just implemented in MATLAB. And if you go to the appendix there, they have some nice tables that are really telling you how to fill in your schema here. So I've only shown you some of the attributes, but you can see here this is like your bus table, and it tells you all the kind of guys and roughly what they are. And then similarly for generators, branches, and so on. So we just kind of built AQL, or CQL, sorry, it's evolving as well, models for these guys that let you, and basically what's nice about this setup is here is like, within MATPOWER, there's already like populated a bunch of like example use cases. And so now you can like kind of pull all these in there and already have a bunch of test instances. So similarly, you go to the next section of the appendix and you get their kind of like description, maybe some other parameters there, yeah? So this is kind of old news, but here you kind of see like the generic setup is that you kind of have some problem specification, which we're going to think of as this CQL schema. Similarly, you just think of your solver as just being characterized by the parameters, and then you get some solution out. So the solution really shares a lot of structure with the problem input, except it satisfies the equations. But maybe over here is stuff like time to convergence and things like that that maybe you want to keep track of, or maybe you don't, depending on what you're up to. Yeah, so what we do, we kind of just build a generic version of this in CQL. So this is kind of like how you would write the paper almost. So it's like the generic kind of power flow setup, kind of describing what are the typical parameters of the problem setup. And then we also create one that's MATPOWER-specific. So really here it's even just like as simple as kind of like attaching the right names to all the variables in this MATPOWER setup. And so here you kind of just specify each of these boxes as their own CQL models, and then here you create functors between them. And then at the instance level, you can kind of like take cases you did here and pull them up to here. And so we played this game also with like another open source tool called GridLabD. It does a lot of other, I mean, of course, MATLAB also does a lot of other things than this, but GridLabD does a lot of other things, but shares an overlap with this, so it's kind of, you can consider it as an instance of the same solver, and in there kind of take simulations or that you did like in MATLAB and then verify them over in GridLabD. So I was kind of like modeling secretary for a DOE project that involved several different groups at academic and national labs, and I was just kind of like, how do you guys exchange models and data? And they were just like long Skype conversations. So we actually kind of got a grad student to implement his kind of schema that he wrote for his custom Julia solver for this kind of stuff. Although they didn't really use it much beyond that, to be honest, but that's okay. So yeah, so here's like where you would normally say, okay, here's my whole zoo of models. But the point is that under the hood, these things are all built up from one another, related to one another by functors or coproducts or this kind of thing. And they all just, and this is also this EISIC tool that they have that you can use as kind of a visualization element within this CQL setup. Okay, 1 minute, well, I'm basically done. So yeah, so just to zoom out here, like in all these standards documentation, you'll find a bunch of information about kind of specifying these models in every layer here. And the problem really is to like enable all these different groups that are kind of doing architectural specifications to reuse each other's models, right? And also to have like a more well-defined and semantic like implementation of what those models really are. So that's kind of the vision that we're slowly working towards. And so this is just kind of summing up, and I know that like there's tons of other so this is like systems engineering, right? These problems are not unique to the domain of power systems. So solving any particular kind of aspect of this could have a lot of impact. And there's a bunch of neighboring communities like this model transformation community that uses a lot of like kind of graph-based specifications, but they're also pretty aware of category theory. So I think Zenovi and Mike know those guys pretty well. So I think we have a lot to learn from them, and in particular, we're really interested in it to like engage with the domain to learn about what's going to be useful in kind of like a CT native tool for this kind of thing. So CQL is kind of like the database level of that, but we want to get to something that really has kind of like components for managing this kind of hierarchical classes and the processes that these guys are all participated in. Okay, so I'll just say thanks there and do one last plug. I'm on an NRC fellowship at NIST, so unfortunately it's only open to US citizens, but we accept applications every 6 months. The deadline's August 1st and February 1st. They're kind of project specific, so if you Google mathematical foundations for system interoperability, you can find that. We'd love to have some new folks in town. So yeah, thanks.
Okay, are there any questions?
Did you show this to the people in the domain actually?
Yeah.
What did they say?
Well, I mean, initially it was like I was kind of partnering with them to also just learn stuff. So it was kind of like in parallel. But yeah, we had one group at UVM where like the computer science guy who was kind of in charge of all of it, like really bid hard. And then like the guy who had to manage the grad students to really do the stuff wasn't as keen on his grad students spending time implementing schemas in CQL. But we did get one of them to do this Julia and MATPOWER setup.
Did you engage anybody in the power industry?
They have partners in the power industry, but no, we haven't so much yet.
So you're talking about models of the engineering aspects of power grids, but power grids also contain some economics as well. Is this something that's on your radar to talk about economic models of power grids?
Yeah, absolutely. I think economic models and also like kind of, information message passing models for kind of enabling this kind of DER setup. Yeah.
Yeah, really important work and nicely done, thank you. So, tiny question. just on the previous slide, you said something about value is spread thin, and I was waiting for what you were going to, what you meant by that.
I was short on time. Yeah, I mean, I think it's just something that, from our experience, people, when you engage with a particular domain, they say right away, like, what is it you're going to do for me? And you say, what is your problem? And neither of you really know what that is, right? So they're like, I think in the end, like, at least for this project, yeah, coming with the power systems people, they're kind of like, what, you're telling us to like do everything in an entirely different way, right? So that's like not really value being spread thing, but I think it's kind of a feature of some of these applications that we're getting into in general in this community, that it's harder to express the added value because maybe it comes from reuse or kind of having this perspective across a number of different domains or projects.
Yeah, but if you're saving people from long Skype calls to transfer address,
Yeah,
clear value.
yeah. No, I agree, yeah.
That was sort of basically my question, but a follow-on question. So does NIST have some kind of strategy for dealing with that? I mean, you hear that in other domains also, in the medical community. Oh, you'll add to my value, find everybody else contributes likewise, so why should I invest? Wait for them to invest, and does NIST have a strategy in this context for addressing
I mean, I wouldn't say NIST specifically does, but I mean, I think Sub on his slides for kind of the selling points for the type of work we do kind of captures a little bit, and then you have to do the work of kind of figuring out which one of those the domain really is having problems with and whether they're aware that that's really the problem. Yeah, but I mean, our strategy right now, I mean, we have this kind of, we funded, or NIST not funded these guys through SBIRs. So like I think having kind of CT native tools or like building infrastructure within existing tools is like a big step in the right direction towards just being able to point to something more specific that really parses for them. Thanks.
Ross, this kind of modeling give you any extra handle on the actual optimization problems in general?
Yeah, so it's not even really an optimization problem at this level, but of course that's what they're all solving. Yeah. So I think that's a slide I pulled, but there's guys who are putting out these Julia power systems libraries from some of the national labs, and they're even just for this power flow problem. I just talked about solving the equations that make it feasible. Then you have all these different classes of optimization problems you find yourself in depending on what you regard as optimal line losses, some notion of cost for this kind of thing. And there's a whole kind of tree of relaxations of these problems, and so now they're kind of like at the point where they're like, these new models are coming into their community by just like demonstrating wins on like these 30 node kind of test cases that are like these old IEEE standards. And so they're already having this problem of like not knowing which ones are really good for what. So I think that's like something that we thought about doing, is just trying to like get in there and try to like just encode the relationship between all those different optimization ones using a similar setup, but trying to get at this like attached computational complexity, I think would be something that's really important in that regard, yeah.
All right. Thanks to the speaker again.